So let me so in the morning we saw, or we illustrated a proof of the following result, that let f1 fk be a function from z mod pz to r, in fact minus 1 1, okay. Phi from to q and k be an affine linear map which is in S normal form, then fk p k, this is less than equal to minimum over I norm fi US plus 1. That is what we illustrated, a proof of it. In the case S is equal to 1, we illustrated a proof. And as I mentioned, that the general case is not conceptually any difficult, it is only the notations which is the issue. So, but the reason why I wrote this is that what it has got, so I should tell you that what it has got to do with our arithmetic progression business. So you remember that we reparameter, so this gamma kf we rewrote as exyz gamma 3f 3x plus 2y or 2x, what was this? 2x plus y? 2x plus y? 2x plus 3y, is it? This is summation j k minus 1 x. So k is 3, 3 minus 2, k minus 2. It should be 2x plus y. K minus k is 3, 3 minus 2, k minus 2, 3 minus 1 is 3, k minus 1, so x minus z and f of minus this thing, minus y minus 2z. Okay. All right. So now, so therefore we rewrote this, reparameterized this 3-term arithmetic progression, and now you see this linear form 2x plus y, x minus z, minus y minus 2z. It is in one normal form. Because if you look at this x comma y, the support of what is this linear form is x comma y. It depends on x comma y. But there is no other form here which depends both on x as well as y. Okay? And then we, okay? So now, what is the advantage of writing in this manner is that now if I write down f is equal to f1 or suppose, okay, let me write g because there are too many f's. Okay. Now if I write down g as g1 plus g2, all the gi's are bounded by 1. Okay. I mean, okay, the absolute constants won't matter, play so much of a role here. Okay. And norm of g2, u2 is small. Then in this, but my claim is that this particular result implies that gamma 3 of g is nearly equal to gamma 3 of g1. How? Because your g is equal to g1 plus g2. Then when you expand, you will get one term is equal to gamma k g1. You will get, and the another terms you will get, there will be how many? At the most, 3 choose 2. 6 terms of the form x, y, z, f1 2x plus y, f2 x minus z, and f3 minus y minus 2z, with one of the fi's at least is equal to g2. With at least one of the fi's will become, so there will be several terms of this form, and with in each of these terms at least one of the fi's will be equal to g2 when I write down. I just write down g is equal to g1 plus g2 and expand it. So there will be a term coming where I take from all the terms only g1, and from the other terms there will be one of the, it will be of the form this, and with one of the fi's is equal to g2. But from this particular theorem, this contribution is less than is small. because norm Gauss U2 norm is small. All right? Because Gauss U2 norm is small, so all this contribution is small. So therefore, that means that this will dominate, and therefore the gamma k f g is nearly equal to gamma k g1. If the Gauss, that is provided that all the GIs are bounded by an absolute constant. But in our result, our applications, the GIs are not absolutely bounded. So when in the case of Roth theorem or Zamiridis theorem, this particular result is sufficient. But for dealing with the primes for finding arithmetic progressions in primes, controlling this is not sufficient, because our functions are not bounded by an absolute constant. They are bounded, but their bound depends upon, because they are defined on a finite set, so of course any function is bounded. But that bound depends upon the prime in the question, which we don't want. Okay, but at least in the case when these GIs are bounded, this particular result is giving us a control, this configuration control. All right. So okay, so now, but I need a similar result for when the functions are not bounded. And then I mentioned to you that you should expect that because we are dealing with the averages, so there should be some conditions which says that if g f need not be bounded, but bounded by a function whose average in some sense is small, then also we can control a configuration. This is all fine to say intuitively, but the exact condition is not so obvious, but this is what I will write. So here this term so you will notice in the literature, the pseudo-random measure is a slightly vague term. I mean, it will depend upon the function satisfying certain number of conditions. For the conditions which I am writing down are the linear form conditions. But if you want to obtain a proof of Green-TAO's theorem using Gauss norm, then actually you need another condition, namely correlation condition. But since we are using this Conlon-Fox-Zhao cut norm, therefore this linear form conditions, what I am writing down, is sufficient. So let dh greater than equal to 1 be parameter. A function v from z mod pz to r plus is said to be d pseudo-random measure of level h if for any affine linear map from Z mod Pz to the Q, Z mod Pz to the R, of finite complexity finite complexity means that this phi and none of this phi and phi j are linearly dependent on each other. Take any two, this phi is equal to phi1, phi q. So any of these phi q's, their linear part are linearly independent. Okay? With Q, R, and the norm of this linear map, all of them are at the most D. We have this gamma phi nu, which by definition is equal to x. All right. So this is, I mean, the generalization of whatever we were calling gamma kf. For this particular linear form, if I consider this affine linear map, I consider V phi1x, V of phi r, Rx, that is equal to 1 plus O, the O of 1 by h. This h will be a function of p. In our practice, we will take actually this h to be what? Log p by log p cube. And but this d will be fixed for us. And this constant will depend upon d. And what is the thing? The dimensions of the domain, dimension of the range, and the norm of this affine linear map should not exceed d. H is the, I mean, the rate at which the error is. All right. So then this is a theorem of Green and TAO, which they call generalized Von-Neumann theorem. So I will write down this statement. So the novelty, I mean, you see, lies in realizing the exact conditions, formulating the exact conditions. You expect, if you go through the proof of Gauss, that there should be a condition so that if the function is bounded by a function whose average in some sense is small, then the proof should still work, but nevertheless you have to formulate the exact conditions and then see that the things work. So the novelty lies of green tau lies in formulating those conditions and then seeing that the actually things works. But the proof as such is not particularly complicated. It is only the notation which makes the life little difficult, which prohibits me from here to explain you the details of the proof because of the notations involved. So given natural numbers S, Q, R, Q, S, Q, R. Sorry, Q, there exists a number D so this S will be the for the how much is the normal form, what exactly the whether our, because as we saw in this, we need the conditions not only on the dimensions of the form, but we also need a condition in order to apply this configuration control thing, that what is the normal form exactly it is in. So basically you can, it is not exactly correct, but you can, I have defined you what is the complexity. What do I mean by a finite complexity? So if phi is in S normal form, then you can say that phi is the complexity of phi is at the most S. Okay. All right. So, and but this is not exactly a definition. Definition generally complexity is defined in different way, but you can, given any that different definition, you can always reparameterize the things so that the things are in S normal form. So given the complexity of the, so this will parameter will be for the complexity. This will be for the domain, the dimension of the domain. This will be for the dimension of the range. This will be for the upper bound for the norm of the things. So given all these things, such that the following holds. Let P greater than equal to D be a prime and phi from Z mod QR be an affine linear map which is in S normal form, and moreover the norm of this thing should not exceed Q. Okay. Let V from Z mod Pz to R plus be a D pseudo-random measure of level H if G1, G R are the functions from Z mod Pz to R such that mod Gi, Gj is less than equal to this pseudo-random measure nu, then plus so if your GIs are bounded by some pseudo-random measure, then you can have this thing control. So now, now the thing is that we have to construct a pseudo-random measure which dominates the function which we are interested in. So the function which we are interested in is this mu a b naught, which could be rewritten as a log n phi w by w, and this a b0 was the indicator function n less than equal to n by w, such that wn plus b naught is prime. A belongs to P1. Okay. This phi w by w I had written, so this w was this product P less than equal to log n by 2 P, and this was written as a phi w by w, here will be log n. Okay, but here it is slightly more convenient if you write down like this, because the function which we will express this factors will get cancelled off. Okay. So then, okay, so now I will consider the first of all the function v tilde from Z, and what the function I will consider is log n phi w by w and summation d dividing wn plus b with the property that support of rho is contained in 1 to r, with r will be chosen less than equal to n to the 1 by 10. Okay. Okay. Why I am okay, and rho 1 will be 1. This is like a sieve weights, but I will choose the weights differently and not exactly the Selbach sieve weights. It will be more convenient for me to choose the weights slightly differently than the choosing the Selbach sieve weights. And why is that the case? I will explain it shortly. Okay. So first of all, let me say that this when I this condition okay. So now if my Wn plus b is a b naught belongs to P1, that means it is a prime and it is greater than n to the 1 by 10, because we considered only those primes which are greater than n to the 1 by 10 in P1. We ignored the few the small primes. While constructing this a b naught, we ignored the primes which were small. We could ignore it because the number is very small, and even if we ignore it, then we will be still left with the positive proportion. So okay, so if in case Wn plus b is equal, so this is v tilde n. So now if Wn plus b is a prime and belonging to P1, now the support of rho only those d's count which are in the support of rho. For the other things it is anyway 0. Right? So now if the Wn plus b is a prime, then only d which accounts for is 1. Because there is no other prime, there is no other d which is in the support and which is of rho and which is dividing Wn plus b, because Wn plus b is a prime greater than n to the 1 by 10. Okay. So in other words, the construction immediately tells us that mu a b naught is less than equal to v tilde n. And also this is less than epsilon n to the power epsilon. I mean these factors are not more than n to the epsilon, and this is at the most the divisors, number of divisors, because I will choose my row also to be row such that this is less than 1. It will be bounded by an absolute constant. We will choose a row so that it is bounded by an absolute constant 1, which will ensure that this v tilde n is also bounded by number of divisors of wn plus b into log n factor. So number of divisors, w is going up to at the most n is going out at the most n, so n is square at the most. So the number of divisors will be at the most n to the 2 epsilon, which is basically n to the epsilon. My claim is that this e to the n belongs to m to the q, v tilde n, this is actually equal to c to the r plus o of od log n to the cube by log n. Claim. No. If Ei's are the affine linear maps from z mod q, z to the qz to z to the r, for any and of finite complexity, then this is equal to this. Then I can, if once I have this, then I will just choose my v to be v tilde by c. There is also the thing that once I have got for the z, I have to transfer it to z mod pz, but I don't think that I have time to give those entire details. So let me, okay, so I will do some of parts of the calculation. In particular, I will explain to you that what kind of weights are convenient for me to choose. And okay, and the other thing is that why is the finite, where the finite complexity condition is being used in proving this claim. Okay. For any affine linear map whose norm is bounded, the domain q and r is less than equal to d. Okay. Dimension of domain, dimension of range, the norm of the affine linear map, all are at the most d. So this d is for the all those upper bound for all those things. Complexity of the normal form of the linear form do not appear into the picture in this particular claim. Okay. Once I have, what I am saying is that if I then if I take v is equal to v tilde by c, then it will be exactly equal to 1. If I replace V tilde by V is equal to V tilde by C, then it will be exactly equal to 1. Then it will be the C, because there are many things and there are, so therefore, and of course, very important thing is that where C is strictly greater than 0. Yeah, I won't do the complete calculation, but if you do the complete calculation, there will be certain integral, and which will be required to prove that it is strictly greater than 0, and that will require a small work to do. So in order for me to prove these things, there is this factor which are floating around. They will anyway come out. So it is better to just define this function lambda n to be the summation d dividing wn plus b mu d rho d whole square. Okay? There is no point in me keeping every time rewriting this phi w by w log n to the power r. Otherwise, I have to keep on rewriting that part, multiply. So I have to compute this is what I have to compute. Summation d dividing w phi n plus b. Because I have to this lambda phi n is what it will appear now for me. V tilde phi n, so therefore this lambda phi n's. And how this dependence on phi n is that d dividing w phi n plus b. Mu d rho d whole square. Okay? But this is equal to what? Summation d dividing di1, di2 belongs to 1 to r, 1 less than equal to I, less than equal to small r. Okay? Maybe a slightly bad notation that I am denoting the support of rho and the dimension of domain range both by r, but one is capital, one is small. Okay? Product mu di1, mu di2, rho di1, rho di2, and 1 by m to the q summation n belongs to m to the q w phi n plus b is congruent to 0 mod di1, it is congruent to 0 mod di2, and for all I. This is, I am just rewriting, expanding and interchanging the summation. Okay? So this mu di1, when you do the square, there will be mu di1, mu di2 coming from them, and rho di1, rho di2 coming from them. and I okay, product of the mu d, and I need to consider only di1, di2 belongs to 1 to r, because that is, if outside the support of rho, I don't have to worry about this d. I have to look at the d, the sum of the range of the d will vary only in the support of rho. And when you interchange, then w phi n plus b is congruent to 0 mod di1 is congruent to 0 mod di2. So now 1 by, okay, so now I can, if the di is a, so therefore w phi n plus b should be congruent to this number as well as this number. That means it is congruent to 0 mod LCM of them. Okay, if this one particular number is congruent to 0 mod one particular di1, di2, so let di is equal to LCM of di1, di2, then what is this? This is thing is equal to 1 by m to the q, the inner sum, okay. So this n is by the way varying over z to the q. This is, I means, in the box n is equal to n1, n2, nq belonging with each ni's. Okay, so now fine, and w phi n plus b is congruent to 0 mod di. Now let d, so I have taken the LCM of these things, so let d is equal to LCM of d1, d2, dr, okay, and w di1, di2, sorry, d1, d2, dr is equal to number of z mod dz to the q such that okay, and alpha d1, d2, dr with this w d1, dr divided by d. So what I'm going to do, this divide the box into in every direction, so that I mean, if you have these things, so I have to, so let's say q is equal to 2. I have to go from here to m, in this direction also m. So what I do is I divide this into the everywhere the box of the length d. 1 to d, here also 1 to d. Okay, here also box, this box, this box, this box, this box. Okay. In each of the boxes, the number of solutions will be the same. Okay, for this particular thing. as you do in Sieve. And all right, because this is a congruence condition. But there will be a last box which will be left because M is need not be a multiple of D. So basically what you will get is the following, that this will be equal to alpha D to the Q, alpha D1 DER plus O of D by M. Okay. And okay. Yeah. Okay. Yes. We all have got tired, I see. It appears to me. All right, so let me just write down the things what we will get, ignoring the error terms, and then maybe I will stop. So you see that. So when you rewrite, this will be ignore the error term. This can be controlled. di1, di2, all right. So now there is this thing, Mobius function is a multiplicative function. This function alpha will be a multiplicative function using Chinese remainder theorem. And since the Mobius function comes anyway, all these di's I have to consider only those ones which are square free. Okay? Only these fellows rows are there which are not multiplicative. If you have a sum of a multiplicative functions, we are very happy that we can write down them as a product. Extend it, hopefully the series will converge, and write down as a product of that, as an Euler product. But at this moment, this function rho, which has a support in 1 to R, it now is not necessarily a multiplicative function. So what do I do about it? So I will, here the Fourier inversion helps. And this is a trick which is not only used here, but it is used in many places. So let f be a C infinity function with a compact support. In fact, I will assume the support of f is contained in -1 to 1. With f0 is equal to 1. And its Fourier transform has a good decay. Exponential decay. Exponential decay is, I take so that I will get a good error term. slightly better term, but the polynomial decay will suffice actually. Okay, and then I will choose my rho n to be equal to 1 by n to the power 1 by log r f of log n by log r. Okay. What is the advantage of choosing this function in such a funny manner? Because now f of x is equal to what? This is equal to minus infinity to infinity f at j e to the power minus ix xi d xi. Maybe I am missing certain factors of 1 by 2 pi somewhere. Okay? No, I am not missing. Huh? Inverse. 1 by 2 pi here, and here should it be 2 pi? Okay. So, all right. So now what is the advantage of this? When I write down this f of log n by log r, okay, then what do I get? I get minus infinity to infinity f at xi by 2 pi. This fellow does not depend upon n. And then you get n to the power minus I xi by log r. Okay. And since I have, okay. So now you see, the point is that this is a multiplicative function. I should have written rho d actually, because this n, okay, this is a one variable thing. Okay. Then you can interchange the sum, and this is 1 by d to the power 1 by log r is for the technical thing because of that. Okay. So 1 plus I xi by log r, and so that it is alpha at the primes will behave like a 1 by p of the form, and so therefore that's why you have to choose the weight in such a manner. It's taking with the help of a smooth functions rather than choosing the weights as you choose in the Selbach sieve, so that this rows becomes multiplicative and you can interchange the integral under summation and it becomes an Euler product, and you can play around with it and to get the result. Fine. Okay. As I can see from the faces that everybody has got tired. So now there is absolutely no point in me making any further remark, however important it may be, because it is not going to go anywhere. Fine, I stop here.